In-class activity 18C, graphing rational functions. At the end of in-class activity 18B, we identified three intervals of the rational function f listed here that still need to be analyzed to determine whether there was a maximum or a minimum value in the interval. Those three intervals were negative infinity to 2, negative infinity to negative 2, negative 1 to 1, and then 1 to 4. Of the three, which one is most likely to contain a possible maximum or minimum, and why do you think so? Well, the interval that might have a max or a min value, I'm thinking is 1 to 4. There's two roots in this interval, so in order to go through or touch both roots, the graph must have a turning point between them. Also, the other intervals are always increasing or always decreasing, so I'm thinking between 1 and 4. Objectives for the activity: you will understand that an appropriate viewing window can aid in analyzing a rational function. A hand-drawn graph may be better than a computer-generated graph at visually showing all the important features of a rational function. You will be able to create a hand-drawn graph with non-constant scale that shows all the important features of a rational function. 2. Consider the interval 1 to 4. Part A. To determine whether 2, 0 is a turning point, determine the sign of f to the immediate left and the immediate right of the point. Is 2, 0 a turning point? How do you know? Well, let's go. I have this graphed from before, so let's go here. I have it entered on Y1, and instead of graphing this, let's go to the table, and I'm going to put in some values. So if we're thinking the 2, 0 is a turning point or could be a turning point, one way to decide would be to take a point just to the left of this and look at whether it's positive or negative, and then we'll take a point just to the right of 2, 0 and see, whoops, didn't want the plus sign, whether it's positive or negative. And it's negative, so there's opposite signs. So this curve is actually cutting through the axis. It's coming down, high on the left through the point and then continuing down to the lower on the right. So it's not a turning point. Let's go on to part B. So we'll go back to the paper. Let's see. I guess, let me write this down here. So let me write this down. It says, we'll put like, not a turning point because, let's see, the sign of f of x on the left of the point 2, 0 it was positive, and the sign of the function on the right of 2, 0 was negative or is negative. So our curve is going to go through 2, 0. Let's go to part B. Part B, it says to determine whether 3, 0 is a turning point, determine the sign of f to the immediate left and immediate right of the point, and we're going to do the same thing. So I'm going to go back to the calculator, and let's do this. We're working with 3, so let's try 2.9, and we have a negative output, and then 3.1 is just to the right of that point, and we have another negative output. So that tells us that this is a turning point. So part B would be yes. It is a turning point. We'll put point because the output on both sides of the point negative. Okay, part C. Is there a max or a min value in the interval? What is the value and where does it occur? So for part C, we're being asked, is there a max or a min value in the interval? And part D, I'm going to do both of these parts together. So if this, here's our x-axis, the horizontal axis, and we have the point 2, and we have the 3 here. We said earlier that the sign of f was positive just to the left of 2, and then the sign just to the right of 2 was negative. So that told us the curve was cutting through the axis right at 2. And then if we do the same reasoning with 3, just to the left of 3, we were negative, and just to the right of 3, we were negative. So with this curve, it's all one piece. So, I mean, it's all one curve. So to actually fit this all together, you can see, you know, what's happening here. It's going to bounce where 3 is, and it's going to cut through the axis at 2. We also have vertical asymptotes just to the left and to the right. So the curve is going to follow the asymptote, you know, up there to the left and then down to the right. So that's part C and D together. Part 3, graphing rational functions by hand is often better when trying to understand the behavior of the graph. Using all of the information we have obtained, graph the function by hand. Okay, so part A says the roots of the rational function, and we already knew this, 0, 0, the origin, 2, 0, and 3, 0. And let's begin by graphing those. All right, so for part A, we're going to start by graphing the roots. So we need to set up the axis here, and we have roots at 0, 0, 2, 0, 3, 0. Part B, it says the horizontal asymptote was located at y is equal to 1. So there's the line y is equal to 1. The vertical asymptotes were when x was equal to negative 2, x is equal to negative 1, x is equal to 1, and 4. Okay, so oops. It's going to continue the axis down here. So there's the vertical asymptotes. And let's see, part C. There's a local max we found in the interval between negative 2 and negative 1. And it was pretty low on the graph, but it came up like this and then went down. There we go. We had another max. We just drew that up in the other interval at the top. We knew we had the curve that came down here, cut through 2, turned around, bounced off 3, and then followed the asymptote down toward the ground there. And we could do the same thing with if we plugged in some numbers, we went back to the table and plugged in some numbers that were less than negative 2. What we would find out is there's a part of the curve that looks like this here. And let's see, this would come down here like that, just plugging in some values, and this part of the curve would go like that. Okay, so part 4. Let's graph by hand functions listed here. It's going to slide it up a little bit, and we are going to need a set of coordinate axes. So let me get that started. So there's our vertical and horizontal axes. Notice we have a x minus 3, the linear factor, linear term x minus 3 in both the numerator and denominator. So it's going to indicate we're going to have a hole in our graph. And let's see that other parts of the denominator. Let's put in the vertical asymptote. So we have x plus 2 in the denominator. So it looks like at -2. Whoops, I didn't mean to do that. X equals -2. And then let's see the other denominator piece, linear factor 2x minus 1. It's going to give us a vertical asymptote at 1/2. There we go. So -2.5. And there we go. We have, let's see. If we take some values and just plug them into our calculator, just a little bit less than -2, to see what the behavior of the curve is around the asymptote. Let's go ahead and do that. So I have the function already entered in here, and let's just go ahead and say, how about -2.1? So 96, that's sort of a large number. I'm just going to try, how about -2.5? It's coming down rather quickly. How about -3? Okay, coming down even more. Just do one more, -5. Coming down, okay. So let's see, we're going to be positive anyway. And if we, something that we didn't do, looks like we're going to have asymptote here. And the curve, just looking at the numbers from our table, the curve is going to come down and do something like this. If we do the same thing, just plug in some numbers in our table, we're going to see between the -2 and the 1/2 on the x-axis, we're going to have a, part of a curve that comes up and does something like this here. And let's see, same thing on the right side. If we go larger than 1/2, we're going to get values that are positive and large. They're going to come down here, and there is actually going to be a hole in the graph, and we're going to hit the root of 5 and then come back up and follow the asymptote. There we go. That's the end of this video. Thanks.